say it's the last class and the quiz is only on Tuesday, next Tuesday. So there's still 1 week's time. So I'll probably hand over an assignment tomorrow, and then I'll announce the portions depending on what I think is appropriate for first quiz. But you should pay attention to whatever is going on in the class, whether it is there for first quiz or not. Right? So yesterday I want to correct an error because I think in the hurry towards the end, I wrote ds by dt as integral t1 to t2 qr by t dt. This is not correct. Both sides obviously it has to be integrated. So clearly, a very explicit way of representing the second law of thermodynamics for reversible processes is through this equation, where it's very much clear everything is a function of time. The time rate of change of the entropy, the rate at which heat is being added to the system, divided by the absolute temperature. Right? This is also S is a function of here regarded as a function of time, and so the derivative makes sense. You're differentiating a function of time. QR is a function of time. The original model gives a concrete model where you can establish what QR is, lambda v times v dot plus cv times t dot. Right? So that you should always have that in the back of the mind, even though we don't explicitly put that here. It's a context in which the second law was discovered for reversible processes alone. That's very important. And temperature can also vary with time, but here the temperature is only one temperature required. Again, the assumption, classical thermodynamics, uniform, homogeneous body. That means body can be heated, and its temperature can rise, but its temperature rises instantly to the same extent at all points within the body. So there's only one temperature for the body as a whole. This is not typically what happens, right? Depending on the conductivity and so on. There could be gradients, but that is avoided. So this is for reversible processes. So I can integrate both sides, because both sides are functions of time, between two times in a process undergone by the body, right? So from T1 to T2, if I integrate, I get this. So we do away with all this delta Q and delta S and all that. It is very clear in its meaning. Now, clearly, this is nothing, this integral is again the integral of a derivative. So this is clearly S2 minus S1, which is what I am going to call as delta S, the left hand side. The integral of the time derivative of S, right? So that will give the function itself, but it's now evaluated between the 2 points. This is actually S at time t2, S at time t1, the entropy of the body at the end of the process, and at the beginning of minus the entropy at the beginning of the process. That's what it means. S2 means S evaluated at time t2, right? So that is what this is, and now this we cannot do anything with this as of now, because it's an integral. If QR is given, I can evaluate that, and the whole details of the process are given, I can evaluate. But here my idea is to avoid getting into the details of the process, right, or even the path. So what I assume is a constant temperature. If I assume the temperature of the body remains the same throughout the process, it's a very special kind of process. It is receiving heat, but the temperature is remaining. That means it's probably kept in a constant temperature bath, right? Very special process. But anyway, at that point, I can take the temperature out of the integral and write it as 1 over T integral T1 to T2 R, which is nothing but the integral T1 to T2 R dt gives the net heat added to the body over the course of the process. So I can write this as Q over T. So for a constant temperature process, for reversible processes, we get the integrated expression as delta S equal to Q over T, which means Q is equal to T times delta S. So we're just looking, somewhat maybe artificial, we're looking at some special kinds of processes where the state functions, changes in the state functions, are related to the heat or work interaction, which we normally calculate using thermodynamics of processes, we saw that even if the process is not reversible, the first law of thermodynamics is for an adiabatic process, the net work done by the body is a negative of the internal energy change. Right? We have seen that. So we saw that that's probably a more important result than this. So this is very much restricted to reversible processes and to constant temperature processes alone. If you want to relax the restriction of reversible processes and still retain the constant temperature limitation, then I can write the second law for irreversible. This is a Clausius inequality, but you should understand that this also has a limitation. Because typically in an irreversible process, you will invariably find temperature gradients within the system. So this inequality applies only to irreversible processes, where again the temperature is the same at all points during the course of the process. And further, now the moment we go to irreversible process, the original model of QR no longer applies. So the Clausius inequality was only a plausible inequality proposed by Clausius to free thermodynamics from irreversible process. But Clausius himself, even though he talked about phenomenon of conduction, never gave any model for QR when the process is irreversible. So how would you model conduction using this? It's actually not quite possible. You have to move away from the restriction of constant temperature. So this applies to a very special case of irreversible processes where the temperature of the body continues to remain uniform. The process undergone by the body need not necessarily be reversible, right? But in this now, if I further impose the restriction of constant temperature, right, then I can easily show that delta S becomes greater than or equal to Q over T, or rather Q is less than or equal to T times delta S. So rather than an equality, we can only say an inequality. Of course, the equality applies to reversible processes, to equal to T times delta S. But if the process is not irreversible, so Q equal to T delta S would be for reversible. Q less than T delta S is irreversible. So here, I can then say that the quantity T times delta S, because here we are talking about how to access the heat and work interactions through quantities involving functions of state, right? So here, if you look at this, Q is less than, so I can calculate delta S provided the end and initial states are equilibrium states. I can calculate delta S using the methods we have used, right? And then if I know the temperature which remains constant throughout the process, right, I can calculate T times delta S, but that is not, I cannot say definitely that that is equal to Q. All I can say is that the amount of heat that is added is less than that. We don't know how much it will be less, right? So this will not give you further information because it's only an inequality. It doesn't help you to exact, but it puts what can you say? This is a upper bound. So T delta S acts as an upper bound to the heat added when the process is irreversible. So we get bounds on the heat added if the process is irreversible. Whereas in the earlier case, it is clearly a more powerful result. An adiabatic process, irrespective of whether the process is reversible or irreversible, minus delta E will give you the work done by the body. So you have to know the importance of these. Now we'll take a look at when the Helmholtz free energy will be of importance. How that can give estimates of work. Right? Before that, maybe I look at enthalpy. So now I consider a constant pressure and irreversible process. These are some very standard stuff found in books, so I'm just going through it. How really applicable to how much, how many of these processes are actually useful that I'm not going to go into, but it gives some significance for these state functions. Right? I think Gibbs probably called the enthalpy a heat function or something, and now you will see why he did that. Because now I consider constant pressure reversible process. So if you look at calculate the delta H, right? So I calculate H2 minus H1. Now the H is E plus PV, right? So what would be delta H? Delta H is delta E, so that would be E2 minus E1. So H2 is E2 plus P2 V2, right? And H1 is E1 plus P1 V1. If I subtract, I get E2 minus E1 plus P2 V2 minus P1 V1. That's what I get normally. So since I'm assuming it's a constant pressure process, so I will write this as 3 times P2 minus P1. So that is where I am using the assumption of a constant pressure process, right? So far nothing has been said about whether the process is reversible or irreversible. So all I have made use of here is the fact that it is a constant pressure. Now if it's a reversible process, constant pressure, then work is given by integral PdV. Because we know reversible work is integral PdV. The constant pressure means integral PdV is P times V2 minus V1. So I can replace this. I make now further assumptions. It's constant pressure plus reversible. That's where I am introducing the reversible assumption. So I can write this as delta E, right, plus W. Delta E plus W. Now what can you say about delta E plus W from the first law of thermodynamics? Equal to Q, right? That applies for reversible as well as irreversible, but here I am concerned only with reversible. It applies to that case also. First law applies to both reversible and irreversible, so this is equal to Q. So we say that in a constant pressure reversible process, the change in enthalpy, you have to always keep in mind these qualifications. In a constant pressure reversible process undergone by the body, change in enthalpy is equal to the net heat added to the body. We may call enthalpy as some kind of a heat function in that sense, right? That gives some relation between the heat and the enthalpy change in a very special kind of process, constant pressure reversible. The first recollecting the internal energy gives the work done in an adiabatic process, no restriction, reversible, irreversible, constant pressure, constant temperature, nothing is there, only adiabatic. That's clearly the most important problem, the most useful result. Then we come to a constant temperature reversible process, then T times delta S will give you the heat input. If it is not a reversible but is a constant temperature irreversible, then the T times delta S will give an upper bound to the heat added. You come to constant pressure reversible process, then the change in enthalpy will give the heat added. Now let's look at an expression for the relating the work and the Helmholtz free energy. So we will see that. So here I will now consider a constant temperature process. So far nothing else. We are not saying whether it's reversible or irreversible, but all through we are here actually considering a homogeneous body of fluid in this case, right? So what I do is that there is only one temperature for the whole body. It's not just constant temperature throughout the body, but that temperature remains the same. So let me now calculate A2 minus A1. You will see why I am doing this. So A2 minus A1 is E2 minus E1, because A is E minus P is A2 minus A1 is E2 minus E1 minus T1 S1 T2 S2 will come, but if temperature is the same at both the end points, then I can write this as minus T times S2 minus S1. Okay. Of course, as of now, I have only required that the temperature at the initial and final points are the same. I haven't said it should be the same throughout the process. Now you will see why that constant temperature through, because here I am talking about A2 minus A1. A at the final state minus A at the initial state, right? So A2 is E2 minus T2 S2 A1 is E1 minus T1 S1. So if T1 is equal to T2, this is correct. T1 equal to T2 equal to T. So far I have not said anything about what the temperature should be in between. No restriction as yet. But we see why that is required. But I can write this as delta E minus T delta S. Now I am going to use that other result where this one, Q is less than or equal to T times delta S. Now I bring in the restriction, the temperature has to be the same T throughout the process, not just at the initial and end points. When I do that, I can then relate the quantity T times delta S to the heat interaction. So if Q is less than or equal to T times delta S, with the equality sign holding for reversible process, inequality for any process, any other process. Right? So I can write this as less than or equal to. So what can I say about this? So I am subtracting T delta S. So clearly T delta S is greater than or equal to Q. Right? So what can I say about delta A? Right? Minus, I am subtracting some quantity which is greater than or equal to Q. So if I were to put delta E minus Q here, what would I get? Would I get greater than or equal to or less than or equal to? Greater than or equal to, right? Because when because I am subtracting, if T data is greater than Q, I am subtracting a greater number here, right? Probably the easiest is to see delta S is equal to delta E minus delta A. If T delta is greater than or equal to Q, then delta E minus delta A greater than or equal to Q. Right? I think sometimes it's a bit difficult to think whether it's less than. So I'm just proceeding in a more a systematic way. Right? So T delta S is this. That is greater than or equal to Q. So I am fine now. So let me rewrite this. So what can I say about delta A? So I bring it over there. So I get delta E minus Q is greater than or equal to delta A. They are just moving terms. I am not multiplying anything by. If I multiply in an inequality, if I multiply something both sides by, let's say, a negative quantity, then I have to change the order of the inequality. Right? So here I am not doing that. Delta A minus Q is greater than or equal to delta A. So I can write this as delta A less than or equal to delta E minus Q. Now I know that Q minus W is delta E. Delta E minus Q is actually minus W. So I get that delta A is less than or equal to minus W. Where again the equal to sign applies for a reversible. The less than will apply for a irreversible. Right? So you have to watch out whether I have done it correctly. So I calculate, I want to use this. This is a valid only for a constant temperature process. Right, so I've got this, so I've expressed this, and then I'm simply making this greater than or equal to Q, so I get this, and then I'm just reversing this, greater than or equal to delta A is less than or equal to, this itself is equal to minus W, so I get delta A is less than or equal to minus W. Now to interpret this properly, I'll consider two cases. One, where work is done by the body, right? Net work is done by the body. Because I will get confused as to what this means really, right? Because W is work done by the body. If that W turns out to be negative, then net work is done on the body, right? So that's automatically incorporated, right? So when I say minus W, it means negative of the work done by the body. It doesn't say anything about whether net work is done by the body or not. It depends on the situation. Right? So let's now consider two cases. Right? First case is when W is actually less than 0, or rather greater than 0. So net work is done by the body. Right? W is greater than 0. Right? So I will now multiply both sides by -1 and write this as W. I can do it irrespective of whether W is greater than 0 or not. If I now multiply both sides by -1, right? I have to change the order of the inequality, right? So I get delta A greater than or equal to W. That's why I'm doing it first. I'm multiplying both sides by -1, right? So minus delta A will become greater than or equal to W minus delta A. So what can I say about W? W is then less than or equal to minus delta A. This is true whether W is greater than 0 or less than 0. You have to understand that, right? So I have now written it in this way, right? So now let's consider W is greater than 0. What it really means, W is greater than 0, that's why it's called as a free energy, because that's the energy available to do work, right? So the body does work, it's going to use some energy that will be clear from the equation, right? You can really see, if you consider the reversible process, W is equal to minus delta A. If W is greater than 0, right? That means minus delta A is greater than 0, right? That means A1 minus A2 is greater than 0. So minus delta A is A1 minus A2. That means A2 is less than A1. So the body has lost some free energy. That makes sense in the fact that the body has done some work and it has lost some energy. It's true of the internal, here it is not the internal energy but the Helmholtz free energy, because we are considering a special kind of constant temperature process, so that's where the Helmholtz free energy comes into play. So what we are seeing then is that the minus delta A, so the quantity minus delta A, right? So now minus delta A is going to be positive, right? So W itself will be positive, but it's less than or equal to minus delta A, which is also a positive quantity. So minus delta A, you can say, provides an upper bound to the work done by the body. So what we can say is that, suppose, now I just pose the question differently. I'm considering a body undergoing a constant temperature process. It starts from state 1 and it reaches state 2, let's say. Now I calculate the free energy change minus delta A. So I calculate A1 minus A2, which is equal to minus delta A. Right? Now net work is to be done by the body during this process. That's the case I'm considering. This is clearly greater than 0. So the body has initially some free energy, Helmholtz free energy. It has lost some and then it has reached a lower free energy state. In the process it has done some work. However, that minus delta A will not give exactly the amount of work done by the body during this process, right? It will only say that the work done by the body, maximum work that can be done by the body is minus delta A, right? But it could be less also, depending on if the process is irreversible, carried out, then it will give exactly that loss can be extracted as work. That is the way you should look at this equation. When the process is carried out reversibly, which many books say slowly enough, so that it's reversible, then this exact matching of the loss of free energy, everything will be converted to productive work. However, the processes cannot be reversible, but there is some amount of irreversibility then the amount of work extracted will be less than this decrease in free energy. So that is why I am saying that we will provide an upper bound, right, to the work. We will not give you the exact work, because this is the maximum work that can be done by the body, right? What the actual work will be less depending on the degree of irreversibility. I can also turn this around and consider the case where now work has to be done on the body. Let us say I consider now a case how much work has to be done on the body to move a system. So I now consider the case where W is less than 0. That means net work is done on the body, right? So obviously this will so initially body is in one state and finally it is another state. So when you do work on the body, its free energy will increase. Helmholtz free energy, constant temperature process. So you expect in this case A2 to be greater than A1 or delta A greater than 0. Work is done on the body. Right? So now, if I were to look at what will be the estimate given by this for the work to be done on the body, I look at it this way, minus W. So delta A is less than or equal to minus W, then minus W must be greater than or equal to delta A. So what this means, then the delta A gives the minimum amount of work that I have to do on the body. To move the body from state 1 to state having a higher Helmholtz free energy, I have to do a certain amount of work, right? But the change in free energy will give the minimum amount of work I have to exert on the body to achieve this change, right? If the process can be carried out reversibly, then it will give that work done. However, if the process is irreversible, then clearly I have to do more work, right? Because minus W is greater than the work to be done on. So I can regard the minus W here together as being work done on the body. It has to be greater than or equal to delta A. So it is equal to delta A when the process is carried out reversibly, but it has to be greater than that if the process, there is a certain degree of irreversibility that cannot be avoided. Then you have to do more work on the body to effect the same increase in Helmholtz free energy. So that is how you have to interpret these equations. Are there any questions on this interpretation? You have to look at it that way, because the equations are the same. Delta A less than equal. If you understand what delta A is, it is always A2 minus A1. And if you know the meaning of W, as far as our sign convention is concerned, W means work done by the body. It can be negative, it can be positive. So I am considering that way two separate cases so that you don't mix up everything. Right? So work to be done by the body, then that would lead to a decrease in free energy, and then you get a upper bound for that. Work is to be done on the body to effect a certain increase in free energy, and again you have an inequality only. The reversible process will give exactly the amount of work that has to be done, but if the process has to be irreversible to some extent, then you have to do more work to cause the same increase in Helmholtz free energy. So that's how you have to look at the equations or the inequalities. Equations are easy to handle. Inequalities you have to be a bit careful how to interpret it. Inequality is there, right? You have to interpret it and give it some physical meaning. Are there any questions? If not, we'll move on to the next topic, which is to look at the equation of state. So far, everything we have done requires the equation of state and the specific heat as the input. Specific heat data is available. We have reduced everything so that we need only the ideal gas specific. Right? So now we have to look at the equation of state in detail and how that is going to help us in calculating all these property changes that we have discussed, for which we have derived all the formula. That is the one point that we have to look at carefully, right? Because there is a lot involved in the equation of state and how you use it, right? So the simplest only equation of state that we have so far considered is the ideal gas equation of state. you look at the ideal gas equation of state, it has serious limitations. For one thing, it is a gas throughout, so it cannot represent any real substance except at very low pressures, as we have seen. Right? So if you look at a typical isotherm, that is P equal to constant, it will look something like this, monotonic, with no anything happening actually. Right? So as you increase the pressure, volume decreases and so on. That's what is happening. Nothing else is happening. Now let us consider the first equation of state. Right? We are in the gas state. Now we have to have something that represents first the transition from gas to liquid. Then we can consider liquid to solid. So in that sequence, we are now considering something which is entirely in the gas state, and clearly that cannot represent, the real substances, because we know that real substances undergo phase transition first from the gas to the liquid as you increase the pressure. Right? So this cannot represent that. The first equation that was proposed that represented that is the van der Waals equation of state. We see how it represents that. It has now two terms. The first term is quite innocuous, RT by B minus B. It's almost like the ideal gas except for the quantity B. B minus B. But the most important point, which is often interpreted as representing the effect of attractive forces, is the term minus A by B squared. So I'm not going to go into the physical interpretation. It's there in all the books, you might have already seen it. But what we should relate this to is a typical phase diagram of a pure component system that represents liquid vapor transition. Right? We have already seen when you have two phases, that coexistence of the two phases is represented by a curve on the pressure temperature diagram. Right? So typically, the liquid vapor coexistence will start from a point called the triple point, where all three phases coexist, and it will go all the way up to higher temperatures and up to the critical point, T equal to Tc. This is the liquid vapor coexistence curve. So what that means is that this is liquid and this is gas. Right? So if I want to, for instance, consider a state here, it's a gas state. If I want to convert it to liquid at the same temperature, let's say, convenience, then I have to slowly increase the pressure, and then there will be a transition to the liquid phase. Right? But what typically is up to the critical point is a very important quantity for all pure substances. If you see, there are tables available which will list the critical pressure, the critical temperature, and the critical volume of each and every substance. Data is widely available. So what the critical point represents is that there is no coexistence possible of the two phases beyond the critical point. So what will actually happen is that here I have three phases, then all along this you will have two phases, and you will see that the properties of the liquid and vapor move closer to each other. We've already seen that typically, for instance, if I consider the specific volume, EV is much greater than VL. Specific density of the liquid is more than the density of the vapor, that all of us can easily relate. Specific volume is the inverse of the density. Right? So the specific volume of the vapor will be much greater, but this is actually this much greater holds only near the triple point. As you go towards the critical point, the BV will move towards VL. The two of them will move closer to each other. It's not as if one remains fixed and the other goes towards that. The difference, rather I would say, BV minus VL goes to 0. At the critical point, the two phases effectively collapse. We no longer have two phases beyond that. So this is a picture that all of you must have encountered even probably in your high school days. Right? So it's important to keep that in mind. Right? So now, so the idea of critical temperature is very important. Right? So now if I now plot this, so I now fix a certain temperature, let's say T1. Then I get what is called as an isotherm. Right? So I have P versus V. That's what is called an isotherm. Right? P versus V on a at constant temperature. And if we plot it, typically for a temperature less than Tc, if T1 is less than Tc, then you will get a curve like this. This should not surprise, because you can see if I fix T1 and now expand this, you will see that this will reduce to a cubic in B. That's why the van der Waals equation of state is often referred to as a cubic equation of state. Because at a given temperature and a pressure, the volume will be given by a cubic equation. It's a cubic in B, right? Cubic equation of state, right? So that is reflected here, but not all a cubic equation. There are rules which says when you will have one cubic equation will have three roots, right? There are several possibilities, right? Cubic equation, because we are talking here only about real roots, right? So you could have, if I have one real root, right? The other two will be complex conjugates. That's one possibility. Right? Now, or we could have three real roots, but there's no way you can have just two real roots. That's not possible. Either you have all three being real roots, or you have one real root and two complex conjugates. But here, though, volume, we generally assume is greater than 0. So we have to also get roots. Sometimes we may discard roots because they turn out to be negative or so. Right? So you have to be aware of that. But typically, these are the two cases, and clearly, you can see that if I now call this pressure PA and this pressure PB, there is no problem when you have pressure P less than PA, you have only one root. So I consider a pressure P less than PA. P less than PA. It's intersecting only at one point. Right? So we are getting only one root, other two roots maybe complex conjugate, we are discarding that. Right? We are getting only one real root, that's clear from the picture. Right? So now, if we consider the pressure P greater than PB also, I am getting only one root. Of course, at this point you are getting two roots. You might ask what does that mean, because I just said that you do not have two real roots, but you are getting that here. The other root may be just turns out to be negative or whatever, right? We have to see what happens there. But I am just ignoring what really happens at PA and PB for now. That's not very important. But rather I am looking at what happens for pressures less than PA and greater than PB, right? And there I have only one root. So that's obviously easier to deal with. Now what can you say about a state like this for a temperature T1, right, and a pressure P less than PA? What can you say about that state? Huh? I am asking you, when you say from the diagram, whether you think it is liquid or vapor or gas. You cannot be both. You cannot say it can be either this or that. You have to specifically say whether it is this or that. So also which one you think it is. So P less than PA, do you think it corresponds to a gas state or a gas state? Low pressure, high volume, right? So clearly that would correspond to a gas state. So this is clearly going to be somewhere here. And if I want to fix the temperature, P less than PA is going to be somewhere here in the gas phase. And now the answer to the other question, what about this state, P greater than PB? What do you think it is? It's also single, only one value. Clearly the answer is liquid. You can see the vast difference between the specific volume. Not only that, if you see how steeply rising this is, the liquid is reflective. You know that the liquid almost is treated as incompressible. This is like incompressible because you see the difference in pressure that you exert in this branch, how much change it is bringing about in the specific volume as compared to here, you will see that one has to be the liquid branch, the other is the vapor branch. Now, I am now talking about a particular pressure which lies between PA and PB. Now it intersects at 3 points. Now what can you say about the 3 roots? There are 3 roots now. How would you interpret the 3 roots? Let's take the first one. This one I'll call it as B1, let's say. What do you think it is? Volume of the liquid. So we just started, we said this is the liquid. We have 3 roots, how would you interpret? Okay, first I will give you a clue. We are going to discard this completely. The second root, the middle root, we will discard because you can see this is really we've seen a condition of stability. We've always assumed that dP by dB is less than 0, but there is something unphysical about this. Because around this segment, actually dP by dB is greater than 0. And so we say that we discard that middle root is of no consequence. It doesn't physically represent anything. Right? So I am left with only 2 roots that I have to interpret. So what can you say about those 2 roots? At the same pressure and the temperature, I am getting 2 roots. So what can that correspond to? Vapor liquid you are saying. Okay, so you are saying that this is liquid and this is vapor. So let me now consider another pressure. There are also 3 roots, so redraw the whole thing. So I am considering only so I am considering one pressure that intersects at 3 points. This is gone. I am going to discard. So you are saying this is liquid and this is vapor. Now I consider another pressure where also it intersects at 3 points. Now again I am going to discard this. Now I get 2 more. Right? What will you say about those? Is that also one is vapor and another is liquid? Huh? There's no question of more and less. We have not come to amounts. We are only talking about specific volume. Right? It doesn't say which is more and which is less. Right? Clearly here, I have a state that's called this B1 and BL1. And I call this BL2 and BB2. So I'm having another, you can see that there are an infinite number of pressures between PA and PB for which there will be 3 intersections of the constant pressure line. So for each one of those pressures, I am getting 3 roots. The middle root we are discarding. Forget about it. Even if we discard that, we are still left with 2 roots at each one of these pressures. They cannot all correspond to liquid and vapor in equilibrium, because if you look at this diagram, that's why this diagram is important. At a given temperature, let's now fix the temperature, let's say this is T1. Now I have only one pressure at which liquid and vapor will be in coexistence. But here, if you were to interpret each one of these as liquid and vapor in coexistence, then this would seem to suggest there are an infinite number of pressures at T1 for which liquid and vapor are in coexistence, which is not something that is obeyed by any substance. When I say 100 degrees centigrade for water, the pressure corresponding to liquid vapor coexistence is only one pressure, which is 1 atmosphere. You cannot say there is a range of pressures over which liquid and vapor will coexist. That is not what we observe. Only for mixtures That is true. For each temperature, you can have a range of pressures over which liquid and vapor may coexist, but not for a pure substance. So clearly, there is something wrong in this interpretation, right? That they all correspond to liquid and vapor. So clearly, there is only one pressure. So I have to fix that pressure first before I can do anything else. Because the problem is that between the pressures PA and PB is where the problem is. Other than that, I have only one truth, and we have already established if it is less than PA, I will take it as vapor, and if it is greater, then I will take it as liquid. That's above PB, right? Above the pressure PB. Now, between the two pressures, there is a range of pressures over which it seems like you have liquid and vapor in coexistence. So first, before we fix the state properly, we need to find what is called as the saturation pressure. We'll see then once you find the saturation pressure, because how to find it is also a question. Once you find it, how the interpretation of the region between PA and PB, how that will change, we will see that in tomorrow's class.